say we have two processes A and B, and we have two resources R1 and R2. So, these resources could be anything in the system which have a limited quantity. For example, the resources could be as something as small as a file stored in the disk, or it could be a printer which is used to print, or a plotter, a scanner, and so on. So, essentially the arrow from R1 to A indicates that A is currently holding the resource. For instance, if R1 is the file, that means A has currently opened the file exclusively and is doing some operations onto the file. In a similar way, the resource R2 is held by B. So, if it is a printer, for instance, if R2 is a printer, it means that B is currently using the printer to print some particular document. Now, consider this particular scenario where the process A holds the resource R1 and process B holds the resource R2, but at the same time process A is requesting to use R2. So, essentially the process A is waiting for R2 to be obtained, and process B is waiting for the resource R1 to be obtained. So, to take an example, process A is opened the file and is using a particular file which is stored in the disk, and at the same time, for instance, it wants to print the file to the resource R2, which we assumed was a printer. Now, in a similar way, process B is currently holding this resource, that is using this particular resource, and it wants to open and utilize this particular resource R1. So, what we see that over here we have a scenario called a deadlock. Essentially, a deadlock is a state in the system where each process in the deadlock is waiting for an event that an other process in that set can cause. For instance, over here the process A is waiting for the resource R2, which is held by B. B in turn is waiting for R1, which is held by A. We have a set of two processes A and B, and each process in the set is waiting for the other process to do something, and each process in the set is waiting for the other process to do a particular thing. For example, A is waiting for B to release this particular resource R2, while B is also waiting for A to release the resource R1. So, deadlock like this is a very critical situation that would occur in systems, and when this deadlocks occur, it could lead to process A and B in this case waiting for an infinite time, continuously waiting without doing any useful work. So, such deadlocks should be analyzed thoroughly. So, in this particular video we will see how such deadlocks are handled in systems. Now, in order to study deadlocks, we use graphs like this. These are known as resource allocation graphs. Now, resource allocation graphs are directed graphs used to model the various resource allocations in the system and thereby determine whether a deadlock has occurred or a deadlock is potentially going to occur, and so on. So, in this directed graph, we represent resources by a square. So, for instance, R1 and R2 are resources and they are represented by the square as shown over here. In a similar way, circles as shown over here are used to represent processes, and as we seen before, arrows from the process to the resource, that is directed from the process to the resource, would indicate that a request is made for that resource. For example, over here the arrow from A to R1 indicates that A is requesting for resource R1. Similarly, B in this case is requesting for resource R2. So, these requests are made to the operating system, and if possible the operating system will then allocate that resource to the corresponding process. So, when that happens, the graph will look like this. Essentially, the direction of the arrow has changed. Now, the arrow moves from R1 to A, indicating that A holds resource R1. Similarly, the arrow from R2 to B indicates that B holds resource R2. Now, there are 4 conditions in order that a deadlock occurs. So, we will now look at each of these conditions for a deadlock. So, the first is mutual exclusion. So, what we mean by this is that each resource in the system is either available or currently assigned to exactly one process. So, for instance, over here we have resource R1 which is free. So, it is not assigned to any particular process. So, this is fine, while this is also fine where the resource is allocated to exactly one process. But in order that deadlocks happen, this kind of scenario should not be present, that is, the resource cannot be shared between 2 processes A and B. The next condition for a deadlock is hold and wait, that is, a process holding a resource can request another resource, that is, for example, in this case the resource R1 is held by process A, and while having R1, A is also requesting for another resource R2. So, it essentially holding R1 and waiting for R2. The third condition for a deadlock to happen is no preemption. Essentially, it should not be the case that resources which an operating system previously granted for a particular process is forcibly taken away from that process. Okay? That is, the OS or another entity in the system cannot forcibly remove a resource which has been allocated to a particular process. Instead, processes should explicitly release the resource by themselves. That is, whenever the process wants, it should release the resource by itself. So, a fourth requirement is the circular wait. What this means is that there is a circular chain of 2 or more processes, each of which is waiting for a resource held by the next member of the chain. So, we see over here that we have a circular chain and there is a wait over here because process A is waiting for process B to release resource R2 and process B is in turn waiting for process A to release the resource R1. So, we have a circular wait condition over here. So, these 4 conditions, mutual exclusion, hold and wait, no preemption and circular wait, must be present in the system in order that a deadlock could occur. So, if for instance we were able to build a system where one of these conditions were not present, for example, suppose we built a system where processes cannot hold a particular resource and wait for another resource at the same time. So, such system would never have any deadlocks. On the other hand, suppose a system has been developed where all of these things are possible, that is there is a mutual exclusion when using resources. A process could hold a resource and wait for another one. Once allocated, they cannot be forcefully preempted from the resource, and circular wait mechanisms are allowed. Then deadlocks could potentially occur. So, having all these conditions does not imply that a deadlock has occurred. It only implies that there is a probability of deadlock occurring in the future. So, this being said, a deadlock in a system is a chanced event. Essentially, it depends on several factors, such as the way resources are requested by processes, the way allocations are made for these resources, the way deallocations are made by the operating system, and so on. So, only if certain order of these requests and allocations happen, and only then will a deadlock occur. So, a small variation in the requests and allocations may cause the deadlock to not occur. So, let us see some examples of this. So, let us say we have three processes in the system, A, B and C, and there are three resources as well, R, S and T. So, each process could request and release resources at some time during its execution. So, obviously, a release can be made by a process only after the request is made. So, these requests and release of resources are given to the operating system at various time instance, depending on how A, B and C get scheduled and how they are executed. So, let us consider this particular sequence, that A requests R and then B requests S, C requests T, then A requests S, B requests T and C requests R. So, this is one potential order for how requests occur. So, we can use our resource graphs or resource allocation graphs to view this. So, we see that A requests R and the operating system will then allocate the resource R to A, then corresponding to B requests S, the allocation will be of S will be to B, then C requests T and the OS will allocate T to C, then A requests S. So, there is a line like this, B requests T, there is a line over here, and C requests R. So, we have the four conditions that we have seen in the previous slide that have all been met. For instance, the circular wait we see is achieved here. R is held by A, while A requests S, S is held by B, and at the same time B requests T. Now, T is held by C, while simultaneously C is requesting for R. So, you see that each process is waiting for an other process in this set to release a particular resource. So, we have a deadlocked scenario over here. Now, we will see that if the same requests and allocations are done in a slightly different manner, then the deadlock will not occur. For example, R is allocated to A and then T gets allocated to C, then A requests S and gets allocated to A, then C requests R. So, we have this over here. Now, A releases R. So, there is no more a line over here or an edge over here. Then A releases S and therefore, R can be allocated to C. So, you see that depending on the requests and releases, we are able to achieve a situation where each and every request or release can be serviced by the operating system. So, in such a scenario we have not obtained the deadlock. Now, we have seen that deadlock is indeed a probabilistic event and could occur with some probability. Now, one way to reduce the probability is by having multiple resources present in the system. So, we have seen that this was a deadlock state essentially because A is waiting for resource R2 to be released by B, and B in turn is waiting for resource R1. Now, one way this can be solved is by having multiple resources. While this particular solution will not always work and essentially depends on the type of resources, it may help to some extent. For instance, if we have two resources of exactly the same type, then both A's request as well as B's request could be managed. That is, the resource, if we have two types of R1, or in other words if you have a duplicate of the resource R1, then that can be given to A as well as B. Similarly, a duplicate of the resource R2 can be given to A and B simultaneously. So, what this means is that, for example, we could have two printers present and A can be allocated one printer while B could be allocated the other printer. While this does not completely eradicate deadlocks, it may reduce the likelihood that deadlocks may occur. Now, the next question is, in a system which could have deadlocks, should deadlocks be handled? So, this is a debatable question. Essentially, it is not an easy thing to answer, because the cost of having prevention mechanisms or to detect deadlocks is extremely high, and it will cause huge overheads in the operating system. So, the other aspect, what is known as the ostrich algorithm, is to completely ignore that deadlocks could occur and run the system without any prevention or any deadlock detection mechanisms. So, either choice, that is either having some deadlock prevention or detection mechanisms, or just ignoring the entire aspects of deadlock, would need to be made during the OS design time, or rather the system design time. So, various things need to be discussed before a decision can be made, such as what is the probability that a deadlock occurs? Is it likely that a deadlock will occur every week or every month or once in 5 years or so on? Second, what is the consequence of a deadlock? Essentially, how critical a deadlock could be. For instance, if a deadlock occurs on my desktop, I could simply reboot the system and it is not going to affect me much. On the other hand, if a deadlock occurs, say in a safety critical application like a spacecraft or a rocket kind of scenario, then the consequence could be disastrous. Therefore, we need to argue about these two aspects. Essentially, if the probability that a deadlock occurs is very frequent, then probably the OS would require some measures in order to handle the deadlock. On the other hand, if the deadlock occurs very sporadic, maybe on average once in 5 years or so, then you may not require to have or handle a deadlock in the operating system. For now, let us assume that we need some mechanism in our operating system to handle deadlocks. So, what can we do about this? Essentially, there are three ways that deadlocks can be handled. One is by detection and recovery, second by avoidance, and third by prevention. So, let us look at the first case, that is detection and recovery. And first, how are deadlocks detected? Essentially, for the operating system to detect deadlocks, it requires to know the current resource allocation in the system, essentially which process holds which resources, and it also requires to know the current request allocation by the processes, essentially which process is waiting for which resources, and the OS will then use this information to detect if the system is in a deadlocked state. So, the way the detection could work is by finding cycles in the resource allocation graphs. For instance, if this is the resource allocation graph for the various resources in the system, the OS will detect a cycle present. For example, over here we have a cycle between the processes D, E and G. Then the OS will say that these three processes are indeed in the deadlock state. Now, the other aspect is there could be requests as shown over here, where there is a resource S and it is requested simultaneously by A, D, F and C. So, we see that this is not in a deadlock state, because there is some sequence of allocation of S to all these processes. For instance, one possible allocation scheme for S is that first S be allocated to A, then A will use the resource S for some time, and then after it completes using S, S can be then allocated to C, and after which S is allocated to F and then D. So, essentially the allocation of S could be sequential among these four processes. So, this will not have a deadlock. However, the presence of a cycle in the resource allocation graph will indicate that a deadlock is present in the system. This technique of finding cycles in the resource allocation graph would work well with systems where there were one resource of each type. Now, suppose we had systems where there were multiple resources of each type, then another algorithm would be required. So, let us give an example of how that would work. Let us say in our system we have 4 resources: tape drives, plotters, scanners and CD-ROMs. Further, there are 4 tape drives, 2 plotters, 3 scanners and 1 CD-ROM. Then let us also say that we have 3 processes executing in the system, P1, P2, P3, and this is the current allocation matrix. So, the row 1 is with respect to process P1. This means that the process P1 does not have any tape drives, does not have any plotters, is allocated 1 scanner and no CD-ROMs. Similarly, process 2 is allocated 2 tape drives and 1 CD-ROM, and process 3 is allocated 1 plotter and 2 scanners. Now, this particular set A determines the resource available. Essentially, out of the 4 tape drives that we have, if you look into this corresponding column over here in the current allocation matrix, we are seeing that 2 is used. So, what remains is 4 minus 2, that is 2 tape drives are free and available to be allocated. So, similarly, if you look at plotters, out of the 2 plotters, 1 is allocated and 1 is free. Out of the 3 scanners, we see that all 3 scanners are allocated. So, it is 0 over here. Similarly, there are no CD-ROMs also available to be allocated. Now, in addition to this, we have a request matrix, essentially which process is waiting for what is represented in this matrix. For example, process P1 requests 2 more tape drives and 1 CD-ROM. So, process P2 requires 1 tape drive and 1 scanner, and process P3 requires 2 tape drives and 1 plotter. Now, the goal of having such definitions or such representations of the resources, allocations and requests is to determine if there exists a sequence of allocations of these requests, so that all requests can be met. If such a case is possible, then there is no deadlock present. So, let us see if we can allocate these requests by the 3 processes. So, let us take process P1 and let us see if the request by process P1 can be met. So, it requires 2 tape drives, and we see that 2 tape drives are available. So, this is fine, and 1 CD-ROM is requested, but there are no CD-ROMs available. So, process P1 cannot execute. So, the process P1 cannot be allocated all its resources. So, it cannot continue to execute. Let us see about process P2. So, process P2 requires 1 tape drive which can be allocated to it because it is available, and it requires 1 scanner, but 0 are available. So, similarly, process P2 cannot be satisfied as well, and process P2 will also need to wait. Now, let us see the third case, where for process 3 there are 2 tape drives which can be met, 1 request for a plotter which can be met, and 1 request for a scanner which cannot be met. So, process P3 also cannot be satisfied its requests. So, P3 also will wait. So, P1, P2 and P3 are all waiting for their requests, and therefore, the state is in a deadlock, because none of the requests by any of these processes can be met, and therefore, all the processes will need to be waiting. If we look at another example where there is a small change, we have just reduced the number of scanners required by process P3. So, in such a case, we see that both the tape drives requested by process P3 can be met by the system. The single plotter can be also met, and there are no scanners and no CD-ROMs that are required, and therefore, we see that all the requests can be allocated to process P3. Therefore, P3s can be satisfied, and we do not have a deadlock over here. So, in this way, deadlocks can be detected by the operating system based on the current allocation matrix and the request matrix. So, once the deadlocks is detected, what next should the operating system do? So, there could be various things that the OS could do. So, one thing is that it could raise an alarm, that is, tell users and the administrator that indeed a deadlock has been detected. Then a second way is to force a preemption, that is, you force a particular resource to be taken away from a process and given to another process. For instance, it could be like R2 was a printer and it is currently held by B. So, what could be done was that the printer could be forced to be taken away from B while it is allocated to A for some time, and thus the deadlock will be broken. This is as shown over here. So, B no longer has the resource R2, but R2 is given to A. Then a third method is by using a technique known as rollback. So, with rollback, both processes A and B, as they execute, will be checkpointed. So, by checkpoint we mean that the state of the process gets stored onto the disk. The process executes for some time, and then the entire state of the process gets stored onto the disk. Now, storing the state of the process on the disk will allow the processes to execute from the point where it has been checkpointed, or the checkpoint state. So, as time progresses, more checkpoints are taken periodically, as shown over here. Now, let us say a deadlock is detected after some time. Then what could happen is that the system could roll back to the last non-deadlock state, that is over here. So, how the rollback occurs would be by loading the state of process A and B in this particular example to the last known state, as shown over here. Now, process A and B will continue to execute from this state, and the deadlock may not occur again. Essentially, we have seen that since deadlock is a probabilistic event, by modifying the ordering in which the allocations are made, we could prevent this particular deadlock. A fourth way is to kill processes. Essentially, if process A and B are in a deadlock state, killing one of these processes would break the deadlock. So, typically the lower important